would like to thank John Barrow and Jeremy Butterfield for inviting me to give this talk. For a while last week I was cursing them because I had to learn all this stuff that I didn't know. But then I realized why they invited me, and I think they wanted to give me the opportunity to really talk about bizarre things you can do with gravity, because they know I'm into that kind of thing. And so the structure of my talk is I will talk about constraints on G, and I will go over there and I will point you in the right direction if you want to know a little bit more about that. But really what I want to talk about is the way that you can let G be the portal to understand many things that are going on at the moment in the way that we understand gravity and we attempt to modify it. And just so you know, the base theory is this one. It's Einstein gravity, and you write it out like that, and that's the gravitational constant that I'll be talking about. And we assume that gravity, Einstein gravity, is just this. It's an Einstein-Hilbert term, and it's minimal coupling to matter, and matter can be anything. And the filter that I will use to move away from gravity is Lovelock's theorem, which says that the only second-order local gravitational field equations derivable from an action containing solely the 4D metric tensor plus related tensors are the Einstein field equations with a cosmological constant. So second-order, local, 4 dimensions, metric. That's where you start off with, and that's your base theory of gravity. Now, I just want to mention a couple of things. The first thing is there's something else. This is, the second lecture when you give a GR course and you follow Weinberg is the geodesic equation. Everything comes from the geodesic equation and from coordinate transformations. But it turns out that if you've got varying constants, that changes. And here is just very schematically what happens. If you have a geodesic equation for a particle, and you have your mass there, you know that if you vary that with regards to your particle, you use that Lagrangian to find out what a particle does, you get the geodesic equation. But what if your mass depends on constants which depend on time? Well, then your geodesic equation will be modified. And instead of having your classic geodesic equation equal to 0, you pick up something that looks like a force term. And I'm sure maybe someone will mention this tomorrow, maybe someone has mentioned this before, but this is a real effect in our understanding of gravity of varying constants. And for example, if I were just to focus on the gravitational force, that would come in here as well, for example, in the self-binding energy of whatever thing you're looking at. Now, again, from what I understand, both John and John have mentioned the law of large numbers, and they've probably gone through the argument, and the Dirac argument is probably the simplest one to give, which is that the gravitational constant is surprisingly related to the mass of the universe over the radius of the universe. And if you convert the mass of the universe into a density times a volume, you end up with a density times r squared, but you don't really like putting r's in it, so you rewrite it as a differential operator, and so you get that if there's a fundamental relationship between Newton's constant and cosmology and the scale of the universe, then it should satisfy something like this. And of course, people have gone ahead, and people did go ahead and try to implement that somehow. And the first one was Pascal Jordan. Look at what's happened here. You've added in a field, and this field goes to some power. You've added a kinetic term to that field. And you've also added, when Jordan set it up, he included the electromagnetic field, and he put it over here. And then the argument was, well, we actually don't see very strong variations of the electromagnetic constant. And so we set that to 1, and that fixes this to the theory that we know. In other words, your Newtonian constant becomes this, and there's a kinetic term that looks like that. And it turns out that if you look at these equations, the evolution equation for the scalar field is exactly in the form that Dirac predicted. It's a box of phi equals to stuff, that's rho plus 3p, and that the Newtonian constant is going to be some jumble of constants, 1 over phi naught. So phi naught is directly related to what we would call the Newtonian constant. Now, the key thing here is this thing has dynamics, and it's not only dynamics variation in terms of time. This is a covariant theory. There's dynamics in terms of space. So when you talk about a time-varying constant, you also have to talk about a spatially varying constant. So this is just a fundamental point that I'm sure has been made, that I've just made again.
Could you define
Phi naught will be the solution. You could imagine that this ends up in a minimum, and that it's that value of that constant. So constraints. So this is the summary of the constraints. That constraints are of order, and having read more carefully, I would say that it's 10 to the minus 12 to 10 to the minus 11 per year, g dot over g. And that there are discrepancy in measurements of g that we will quickly look at, which is interesting. And that given that electromagnetic weak and strong forces are weak on large scales, you want to look on large scales. So the best constraints on g are going to be on large scales. Now, if you really want to know about this, the king of varying constants is Jean-Philippe Pouzin, who's written a series of very clear and comprehensive reviews. So if you really want to dig down in what's going on with a fantastic bibliography, you do what I did, which is read this. But let's start off with the value of g. So the classic value of g, it's the, I think, 1790s, Cavendish looks at a torsion balance, and he measures, he puts masses near a torsion balance, measures torques, and he puts a constraint on g. What is fascinating is that over the years and over the centuries, we've perfected that kind of technique. And we can look at pendulum going through masses, we use laser interferometry, and we perfect our measurements of g. And something very interesting happens. Look at this plot here. There's something called a co-data, which is based, I think, in Paris, where they basically collect the values of the constants, and they explain where they come from, and they propose what are going to be the official values of those constants and the uncertainties. And co-data, 1986, that was the value they proposed, and those were the errors. This is co-data 98. The error bars ballooned dramatically by a factor of 10. Okay? And what happens is you have all these experiments which have phenomenal error bars but end up being inconsistent with each other. Okay? And this has gone on from 2002, 2006. The errors from co-data go down and down and down, and you think that you're converging until you look at the latest values. And again, I just want you to look at the highlighted values here, which is the Washington experiment, the Chinese experiment, and the Colorado experiment. And you've got these phenomenal errors here, but they're inconsistent at the level of 10 sigma. Okay? And one way of seeing that is here. Is you have these constraints, and the errors continue to go down, and then you've got these two constraints there which are completely off. Okay? And no one really understands why. They're different experiments, and people have acknowledged that they need to understand what are the systematics. So when you look at something like this, and you look at the errors here, which are of order 10 to the minus 5, but then you actually, or 10 to the minus 4, more like it, and then you compare it to, then you include the uncertainties between the values, we've improved by approximately a factor of 10 from Cavendish's original measurement, which was end of the 18th century. So it's quite surprising how difficult it's been to measure this, the constant and pin it down. And we seem to be making some progress, but we don't really understand how. In other words, you can't take the error bars of individual experiments as the error on the understanding in G. There's some kind of systematic error bar going on. So then you enter constraints on G dot. And I could go in detail into various things. For example, one idea is that you can constrain the variation of the Newtonian constant by looking at temperature variations of the Earth. And the idea is the sun is this machine. It pumps out light. How much light it pumps out depends on the value of the gravitational constant. If the sun was very bright, the Earth would have been much hotter in the past. You can put a constraint on how hot the Earth was in the past by seeing what were the earliest living organisms and the kind of temperatures that they would be allowed, that they could survive in. And a factor of a 20% increase in the temperature of the sun in the past would have wiped out, there would be stuff that couldn't have existed. But just by looking, going further and further in the past and looking for bacteria and how far back they are, you can put an upper limit on the temperature. So that sets a bound. The other idea is that you can look at how the Earth's magnetic field is locked into rocks, and you can put a constraint on the change in size of the Earth due to variation in in Newton's constant. You can look at variations in Earth's rotation, again by looking at coral fossils, which surprisingly I learnt react to full moons, and so there's a clear register of when there were full moons, and you can map out the Earth's period. Of course, the solar system is the great place to do this, right? Because it's in the solar system that you have things like lunar laser ranging, where you have incredibly precise measurements of the motion of the moon. You can take constraints from the Shapiro time delay, and arguably the strongest constraints at the moment are from the solar system. Pulsar timing, pulsars are one of the great sources now for constraining general relativity. And the obvious thing to look at is the change in the orbital decay of these pulsars, and subtract out what you'd expect from gravitational radiation and see if you can put a constraint on just the fact that G is changing. That's been done with the Hulse-Taylor pulsar, and it's of order 10 to the minus 11. This is the latest data from the Bonn group, and you start getting down to 10 to the minus 12 over here, around here. You have stars, of course, and of course the way that stars shine and the way that they pump out light is going to depend on the value of the Newton's constant, the ages of globular clusters. Anyway, there's a list of things there that I could go into, and the constraints, you always end up with constraints of order 10 to the minus 11, 10 to the minus 12. So the number to take away is 10 to the minus 12. Okay, that's the number, and whatever you do, you can't beat that at the moment. Even with the CMB. So, again, the CMB delivered yesterday. With the CMB, how would varying Newton's constant affect the CMB? Well, you've got this exquisite map of the power spectrum of the CMB. This is the angular scale, large angles, small angles. This is the amplitude of anisotropies. The structure of this tells us a lot about what was going on at recombination. For example, if Newton's constant was varying, it would change the expansion rate. It would contribute, for example, if it was a Brans-Dicke field, a bit like radiation, and it would affect the heights and the heights of the relative peaks. It would affect, for example, how silk damping occurs. As the universe recombines, the universe goes through a period where it gets very sloppy. It gets very sloppy. Photons are able to redistribute energy. By redistributing energy introduces a damping tail. The structure of this damping tail will say something about, for example, what is the mean free path at that time, which again is dependent on on Newton's constant. So all these things come into this incredibly precise measurement. And if you go even further back in time, Newton's constant, time-varying Newton's constant, will affect the expansion rate of the universe. The expansion rate of the universe affects the abundances of light elements, and you go down to arguably 10 to the minus 13. And that may be the strongest constraint. It's the most model-dependent constraint, but it's the strongest constraint. So those are the numbers that we're talking about. And I suppose that was the bit that was the difficult bit for me, but I ended up learning quite a lot from it. The not difficult bit for me is using this as a portal to madness, to what people are doing, okay? And so my colleague Tessa Baker has produced this plot which is proliferating through talks at the moment, but here's my turn to use it, in which she tried to structure the genesis or the bestiary of modified gravity in terms of Lovelock's theorem. And so remember Lovelock's theorem, it was four-dimensional, metric, local, what was it? Second order, right? And so she's just branched out and said, well, what happens if you go to higher dimensions? You become non-local, higher order, or new degrees of freedom. And you get this incredible range of theories. For example, Brans-Dicke theory involves adding in a scalar field. But you could add in a scalar field, but you could also add in a tensor field, or a vector field, and we'll talk about these two, or a tensor field. In fact, we'll talk about those three. Starobinski model that John mentioned earlier today would fit in there. It's an F of R theory. I am going to talk about non-local theories that at the moment people are quite interested in, and I will mention, of course, out of respect, higher dimensional theories that have had their heyday over the last decade. The interesting thing is you can look at every one of these different variants of gravity in terms of G, in terms of the gravitational constant. And I will try and convince you that that's the case. And what that means is if I convince you is that you can see that G will be affected by many things. Degrees of freedom, symmetries, mass scales, dimensionality, locality, all these things will affect G in a different in some way. So let me start with Brans-Dicke. So this was the Brans-Dicke theory that I put up. This is the base theory, the base modified gravity theory that everyone works with. And for those of you who don't know that, there's a very nice thing you can do. You can do a conformal transformation. In other words, you redefine your metric and factor out some scalar field. And you plug all that in there. And your action then becomes something that looks like that. So your new metric had that thing in front, and so you're going to pick up some terms from here and some terms from here, and you end up with a ratio with that original field with the conformal field. You pick up a kinetic term, which is having plugged that in here, it generates that, and then you have your original field there, and then you have your matter field. And the interesting thing to note is that your new conformal field is glued to the matter field over there, all right? And then you just say that this field that you had over there is that this was this arbitrary field that you used for the transformation. And you just do a redefinition. And your theory then just looks like Einstein gravity with the kinetic term, but then your matter field is coupled to this thing here. In other words, your varying constant, your theory with a varying Newtonian constant is nothing more than in a different frame, in this transformed frame, as normal Einstein gravity with a fixed constant, but in which there's this time and spatially dependent coupling to all matter. It's universal, but it's just there's a new coupling to matter. And you can constrain this theory, and by far the best constraints at the moment, although some of my strong field colleagues would say that no, we're moving beyond this at the moment, is from the Cassini experiment. It's using the Shapiro time delay. We can constrain this thing to be much larger than 40,000. Note that it is in the limit when this goes to infinity that we recover general relativity, because it freezes the dynamics of that scalar field, and it's a constant. And then you start generalizing, okay? And you start saying, well, actually that constant is not really a constant. It's a function of phi. And you can do that. And then you can try and figure out, you can try and constrain that model, and you find that you can look at, for example, the PPN parameters. This is a set of parameters which you can use, which basically map observations like the Shapiro time delay, the precession of perihelion of Mercury, lensing, to deformations of gravity. And again, you get a constraint like this. But now this is the interesting thing, is that when you start putting constraints on these constants, they're local constraints. So remember that we'd started off with this being a constant. It's not a constant anymore. That became a constant. That's not a constant anymore. And so the constraint on that is a local constraint on a constant which was supposed to fix another constant. So it starts becoming more complicated. And then we really enter an incredible field of activity, which is, well, suppose you write down the most general second order action for a scalar field coupled to gravity. And you end up with this beast called the Hondesky action. And I mean, I could go into it, but I don't really think you want me to. You've got a scalar field here. These things here, these kappas, and this kappa here, this kappa 3, these are functions of the kinetic term of the scalar field and the scalar field itself. You know, it's an enormous beast. And the interesting thing is this action captures a lot of the things that people are working on at the moment, things that you've heard about, Galileons, ghost condensates, symmetry. A lot of these theories fit into this. So, you know, Brans-Dicke theory, you know, this thing which was really seeded by the idea of getting a varying Newtonian constant, is at the moment spawned all this stuff. Okay. Now, two things I want to mention about this route. One of them is, one of the other branches away from Lovelock's theorem is forget adding in an extra field and just putting in higher derivatives. So instead of having an Einstein-Hilbert term, having a function of the Riemann of the Ricci scalar. You could have functions of the Ricci scalar and Riemann-Ricci curvature. You could do whatever, but let's just keep it simple. So your Einstein-Hilbert term wouldn't have this here. We'd just have the R. Let's just make it a function of that. Now it turns out that the field equations look like that. So they're more complicated than the Einstein equation. F sub r is nothing more than the derivative of f with regards to r. And you can see that if you put f equals to r, that's 1, and then other things go away. But again, you can conformally transform that thing. So define a new metric in terms of f sub r times g mu nu, and define a scalar field, which is some bump times the log of f of r. And you end up with scalar tensor again. So again, even that branch of moving away from Einstein gravity is nothing more than a scalar tensor theory, something like Jordan-Brans-Dicke, except it has the interesting property in that the constant is -3/2. And John mentioned this. I thought I was going to mention it, but he had to mention it. That theory, one possibility is that you have that f of r is just going to be the r plus some constant times r squared. I have a mistake in my transparency. This should be 0 for metric. If you want to do Palatini gravity, in which your 2 degrees of freedom are the metric and the Christoffel connection, you get this. And Palatini has died many deaths, one of them at the hands of John Barrow. So the interesting thing I was saying is one of those theories is this r squared inflation, which people were hugely excited with the Planck results, which lies over here, which it seems to lie bang in the middle of these contours. This is the amplitude of tensor fluctuations relative to the scalar fluctuations, and this is the primordial tilt. And so there were a lot of people swaggering around, incredibly pleased with this result. Of course, yesterday that changed, and that thing lies over here. So if this is true, it doesn't look that good anymore. So one of the things that people were doing before the bicep, so there, as you know, there have been rumors about bicep for quite a while, all right? And people kept on saying it's inconsistent with Planck. The key thing about this plot is that these contours were produced by setting the running of the spectral index to 0. That means you just had a constant spectral index across all scales, all right? Now, if you go back to the Planck inflation papers, figure 4 of that plot, of that paper, they produce the same graph in which they have marginalized over running. You allow running, and what happens is that those contours blow up like that. So it's perfectly consistent with Planck, but you have to marginalize over the running of the spectral index. So the r squared as a theory of inflation is not doing very well at the moment. The other interesting thing which arises in these theories, in these scalar tensor theories, and again it has to do with the strength of gravity in G, is what's known as screening. And I apologize that this figure isn't very clear, but a few people have done quite instrumental work on this here at Cambridge. And it's this idea that you can add a potential for that scalar field, okay? And suppose that you transform to the, well, you start off with some theory, you transform to a frame where where the gravitational part just looks like Einstein gravity. That inevitably leads to non-minimal coupling to the matter. That leads to that e to the 2 phi, which you can write this way. And so here's the density, here's the stuff, and you get this correction, and it depends on the scalar field. So the potential that the scalar field actually feels is not this one here, it's this one. And the shape of the scalar, the potential is going to depend on the amplitude, on the size of the density perturbations, which means that the scalar field, which you can think of almost as a proxy for G, has a different value in dense regions as opposed to empty regions. And this is illustrating that if there's a large density, it does that like this, but if there's a low density, it's much shallower, and you can go to different values. And here's an example of what happens if you do that. If you do simulations in which you fix that scalar field to not vary, you get some kind of structure. And this is one of my colleagues at Oxford kindly produced me some figures to show this. But if you include this chameleon mechanism, structures look different. Now, the motivation for this is that, in some sense, to try and solve the cosmological constant problem, it would be great if, in low densities, something strange happened, which is what we would expect to happen now at late times. But at high densities, at early times, everything looked fine, and that's the motivation behind this mechanism. It's known as the chameleon mechanism. Now, I've only been talking about scalar fields, but one of the workhorses for studying something else is what's known as Einstein ether theory. And what you do there is that you want to try and test Lorentz invariance. And you kind of want to build a theory which is fundamentally Lorentz invariant, but which breaks it when you start looking at specific solutions. And this was set up in 1972 to actually do that. And so you have the Einstein-Hilbert term, and then it's coupled to a spin 1 field here, a vector field. And what this is not all the possible combinations that you can make of that. And so you can have alpha contracted with mu, and mu contracted with beta, alpha contracted with that, and beta contracted with that. And you write down all the possibilities, okay? And you add an additional condition, which is, because of isotropy, you want that field to be time-like. So you enforce this condition. Now, the interesting thing about this condition is that hidden in this is a metric. All right? This is a constraint equation, which you could write as G alpha, beta, right? Which means that in principle, for some components of U, you could solve it in terms of G, and you could plug it in here. In other words, this doesn't look like a modification of gravity, but actually, because of this constraint, there are going to be modifications to the field equations. And you do that, and what you find is that the Newtonian constant is modified. The Newtonian constant in the action is here, but it depends on constants that go into that kinetic term, and the constant that goes into the Friedmann equation is different. And what is interesting is that the constant in the Friedmann equation is different to the constant that goes into the Newton-Poisson equation. So here, the gravitational constant takes different values depending on the setting in which you're looking at. And the beauty of this is it's a function of constants of the theory. Now, there are many constraints on this theory, and the latest ones that are, again, by looking at binary pulsars. And of course, if you've got a spin-1 field, you're going to end up having dipolar radiation. And because we've got very strong constraints on the perihelion shift of on the orbital decay of millisecond pulsars, we can put quite tight constraints on that. And these are the latest, tightest constraints from this fantastic group at Montana led by Nikos Younis. Right, higher dimensions. Well, you know, we've been there and done that, right? So the idea is that suppose you look at theory in higher dimensions, in d dimensions, and you decide to reduce it to a 4-dimensional theory plus stuff, okay? Suppose we have a 5-dimensional theory, a la Kaluza-Klein, and we reduce it to a 4-dimensional theory plus stuff. Well, you can write your 5-dimensional metric as a 4-dimensional metric, some scalar fields, and a vector field. And this will be your 4-dimensional components. Then your 5th-dimensional components, which you'll label by Z, will add these things in, and if you expand that over there, a number of things happen. It becomes Einstein gravity plus some extra fields, and your gravitational constant is modified. Now, this was put to fantastic effect in the late 90s by Akani Hamid, Dimopoulos, and Dvali. And what they noted was that there is a hierarchy between the mass Planck and the electroweak scale, as you know. But what if you were able to have the Planck mass to be equal to the electroweak scale, except you have to be clear what is that Planck mass. And so the idea is that you write your higher dimensional theory, which looks like that, and that's your d-dimensional Planck mass. And then you compactify. And remember, in the previous case, a factor of L, the size of the extra dimension, came out in front. So you pick up a volume term over here. And that's the thing which is the measured Planck mass. But actually, the thing that you really want is that the fundamental constant is that thing over there. And it turns out, if you go through the numbers, if you make your d-dimensional mass, Planck mass, equal to your electroweak Planck mass, then you can, choosing the right number of dimensions, extra dimensions, you can make that scale about 1 millimeter. And that generated an industry, and very fascinating industry. What a key thing you want to do is that means that you have to live on a brane. You have to be stuck on this three-dimensional space. And your forces are limited to that, but gravity can go out and in, and a lot was done. An interesting thing is you actually don't need to consider a compact volume. If your extra dimensional space is warped somehow, you can basically effectively confine, you have an effective volume which is finite, and that was proposed by Lisa Randall and Sundram. And here again, this is the metric. This is all old stuff, but if you factor it out, this is your 4-dimensional part, this is your 5th-dimensional direction, and there's a bit that multiplies your 4th-dimensional stuff, which just warps and contracts as you move away from the brane. And so your Newtonian constants on the branes are going to depend on these values and the distances between the branes. Very good. So we're in the final stretch. A way that I found very useful, and I think is a way that people have been thinking a lot about either modifying gravity or modifications of gravity, is through this idea of degravitation. And it's very much one could say that the fundamental driver for this is if you've got a cosmological constant and it gravitates on large scales, you have a problem. Is there a way of just suppressing the effect of the cosmological constant on large scales through gravity? Okay? And that's that means that you start looking at the Newton's constant as an operator. So you've got stuff here, and that's an operator which filters what's going on over there. Another way of thinking about this is you look at Newtonian force, and somehow this is going to introduce some corrections to this on large scales. And there are two possibilities that you can consider. The first is, suppose you take a spin-2 field. Suppose you take Minkowski space and a spin-2 field, and you write down the most general action which satisfies gauge invariance, or the linearized version of diffeomorphism invariance. You pretty much lock down to something like that. And then you decide to add a mass term to that graviton. Well, we have some experience to what happens if you add a mass term to a force carrier. It introduces an exponential decay. So one of the things you can do is you can try and solve that in a spherically symmetric configuration. And so you put in a metric that looks like that. And you solve and you find it. And you have the 1 over r here. And you pick up these exponential decays. And so indeed, gravity is suppressed on large scales. But another very interesting way of looking at this is if you look at it as an analogy to massive electromagnetism. Suppose you write down electromagnetism in this way with a mass term here, and you have a scalar field over here and a coupling here. And then you do the following thing. You solve for the scalar field. Okay? You solve for the scalar field, and you replace it in. And what you'll end up with is an equation that looks like this. You'll end up with an action that looks like this, which there's a correction to the kinetic term. There's no scalar field anymore. And the interesting thing is this is gauge invariant. This has all the right properties, but it's non-local. And more importantly, on large scales, this thing gets small, which means this term gets large. And so on large scales, this is changed. In other words, the effect of this mass is to introduce, in some sense, a high-pass filter. You get rid of the large-scale stuff. Now, there's a whole industry over the last few years of trying to move on from fierce Pauli action and construct something which is generally covariant, ghost-free, and it's a talk in itself. And an example is the Hassan-Rosen bigravity, where you have two metrics, G and F. You have a Hilbert term for that, a Hilbert term for that. You've got two Planck masses here, and then you've got a mass term. And it's fascinating. It's very interesting. I'm not going to go into it, but it's a very active field of research, which quite a few people here know about. But I've touched on non-locality there. So the interesting thing about non-locality is it's the kind of thing that we all avoid, but keeps on cropping up in the strangest places. So for example, there's this magnum opus by some Russians, Barvinsky and Vilkovitsky, who've tried to work out what was the one-loop effective action for gravity coupled to gauge fields. And the basic thing that you see is that because you've got all these massless modes, and you try and integrate out these massless modes, you generate non-local terms. And so the non-local action is the one-loop action for gravity with gauge fields is non-local. It has terms like this, r over box. You even have some log box terms in front. Now this is very interesting if, for example, you want to try and solve the dark energy problem or the cosmological constant problem, because it seems that these things exist. All right, they're in this calculation. And what Stan Deser and Woodard pointed out was that suppose you limit yourself to just these terms. Forget about these terms for now. All right. As I said, this is going to be important on long time scales and large scales. All right. And you can solve this perturbatively. And what you find that this r over box is basically going to be proportional to the age of the universe over equality. And the reason equality is in there is because r is equal to 0 in the radiation era. And you can pick this dimensionless constant to be about 10. And you'll have, without fine-tuning, something that comes into play at exactly the right time. And it's triggered by something we know exists, which is a radiation matter transition. So it's an interesting point. Of course, it doesn't work, right? It doesn't work for many reasons, right? It doesn't work because you can't ignore these terms if you're going to play that game, and these lead to massive instabilities. Not only that, if you ignore these terms and then you work out the details, this doesn't give you the right cosmology. But it's an interesting point to make. It does also make you think of G as, if I factor out R over here and I move G in here, G is this non-local thing, this non-local filter. But then you don't really know how to calculate with, well, you do know how to calculate it, but it's much more complicated than people had thought of before. So one of the things you might think is you can just call this a scalar field, and add it in, and add in a Lagrange multiplier. And so then this looks like just a normal action, the kind of thing we know how to work with. The problem is that you can work out the equations of motion for this, you can vary it, but that's not enough. You actually have to impose extra boundary conditions so as not to violate causality and other fundamental problems. So it's an incredibly rich field, it's an incredibly complicated field, and not a lot of people want to work on it. Okay, in my final few minutes, I've told you about bizarre things that we could do with gravity and which people are looking at the moment, and which I think tell you something about Newton's constant, the way Newton's constant could behave on different scales. I want to finish by talking about extreme observations, okay? And most of the constraints that you talk about in constraining G lie over here. What is this plot? This plot is again, it's become this iconic plot produced by Dimitrios Psaltis, where on the x-axis, you get a system, and you estimate what is the gravitational potential there and what is the curvature there. And so, for example, for the simplest gravitational systems, it's going to be gm over rc squared or gm over r cubed c squared. All right? And you can lay out all these systems where you can constrain gravity on this plot. And you've got solar system constraints, you've got white dwarfs, you've got neutrons, you've got stars over here. What I want to talk about is stuff that happens here, out in the edges, because this is the stuff that's going to be happening over the next few years. All right? So I'm going to start down here. Okay? And I start down here, and an interesting thing happens when you start looking at the very large-scale structure of the universe. It's been mentioned in the talks before. If you look at the very large-scale structure of the universe, we've done a great job at mapping out distribution of radiation through the cosmic microwave background, galaxies, and by analyzing the structure and quantifying the statistics of this structure, we say things about cosmological parameters. Now, the way that we do this is basically where it's incredibly successful is by doing linear perturbation theory around a Friedmann-Robertson-Walker spacetime and cranking through these linear equations and figuring out what the various constants do in there. And you know, a kind of almost cartoon version of that is if you write down your metric, there's going to be the Friedmann bit, the scale factor, and then there are going to be the fluctuations. If you focus on scalar fluctuations, you really only have to talk about two potentials. And it turns out that when you perturb the Einstein field equations, you really only have to talk about two equations, which is a relativistic Newton-Poisson equation that looks like this. This is an amalgama of matter and velocity perturbations. Let me just call that a density perturbation, and a relationship between those two potentials. Well, it turns out that that panoply of theories that I showed you, if you sit down and you linearize those theories, they all look like this. They all look like this. It's a modified Newton-Einstein field equation, a modified matter term, and then an extra tensor, which is going to be linear in your metric perturbations and any extra degree of freedom. And it turns out that in a particular limit, which is actually exactly the limit in which you look at when you look at large-scale structure surveys, the Einstein field equations look like that. So you pick up a modification here and a modification here, and you can formally prove this. And this thing here is going to be a function of scale and a function of time. And so the interesting thing here is that, again, what was Newton's constant in terms of gravitational growth is changed. You now have to constrain this bundle over here. And an example of how you do this is by measuring the growth of structure. And the thing that you do at the moment is looking at something called redshift-based distortions. You look at some redshift at some distance, and you look at the statistical isotropy of a system. And what you, if you're measuring your distance in terms of redshift, and you're measuring angles. If you're measuring the distance in terms of redshift, i.e. velocities, your cosmological velocity will have a peculiar infall superposed on it, and that amount of that infall will corrupt the distance that you measure. So for example, if you were to measure a ball at some distance, you know that if there was a ball of mass here, you know that there would be an infall towards that mass. So what you'd actually see is a squashed ball in that direction. If it was a very nonlinear clustering, the velocities would be so large that they would compensate, overcompensate, and you'd get a finger of God. And we've used this. By measuring this squashing, you can measure the amount of gravitational collapse as a function of redshift. And this is exactly that. This is the amount of gravitational collapse as a function of redshift. And this is the data. And it's pretty inconclusive at the moment, but it's where we're going. And the hope is that over the next few years, we're going to get errors of order 1% from out to redshift 2 on these quantities. Extreme test number 2 is advanced LIGO is about to be switched on. And it's going to see something. Even if it's only neutron-star mergers, it's going to see something. And one of the great things that we can do now is we can actually calculate what happens as these objects fall into each other, merge, and then decay their gravitational radiation. And this is exactly an example, I think, of a binary black hole event where as they fall into each other, you have the in spiral, it falls in, then you reach a point where they completely merge, and then it decays, and there's this burst of gravitational radiation that comes out. And the interesting thing that's been shown over the last 3 or 4 years is that this process is quite sensitive to the theory of gravity you're looking at. And just to give you an idea of the numbers, one will have something like 10,000 cycles from here to the merger. Then one has a few tens of cycles in the merger, and then a few tens of cycles after the ring down. So you've got a lot of information in a very weak field regime. Then you've got a little bit of information in the merger regime and a little bit of information in the decay regime. And that can tell us a lot. And one particular example, which again is related to the gravitational constant, is we think of this gravitational constant as this placid thing, even when we promote it to a field, as this placid thing which is, may have some time dependence, may have some space dependence, but actually it can come alive. And as was shown by Thibaut Damour and Sposito Farese in the early 90s, and I think it was first pointed out by Damour in the 80s, you can have an effect where the scalar field is pretty placid, but once the system reaches quite a strong field regime, it comes alive. It comes alive and gets aligned and has a dramatic effect on what's going on. It's what's known as spontaneous scalarization. And only very recently have people been able to model this numerically and see the effects that this would lead to. And this is an example of that, where you have, I think the red line is just the usual evolution of this is strain versus time. And this is the usual effects that you have. And then you have the green, which is what you would get if you had this spontaneous scalarization. The final extreme observation that I want to point out to is the idea that using very long baseline arrays looking at millimeter and sub-millimeters, you'll be able to map out the black hole at the center of the galaxy, right? Then this is remarkable because this means that you'll be able to map out the shadow at the center of the galaxy. The way that I worked out is about 60 pixels across, okay? So it's a not very crappy image of the center of the galaxy, of the black hole. And the stuff that's going on there, the shadow that's going on there, will say something about the structure of the black hole at the horizon. And it is at the horizon that you expect, if there are deviations, there will be strong deviations. So one of the things that has been claimed is that you can test things like the no-hair theorem, or the fact that the black hole may not have any more information than just mass and spin and charge, that there may be other things, for example, these scalar fields or some remnants of the gravitational constant at some earlier time. And this is really something to look forward to over the next few years. So I think these three things are things which are not often spoken about in the context of a talk like this, and it really is something to look forward to over the next few years. So I'll finish with this. There are current constraints on G, but they're uncertain. I don't know why. There are limits on the time variation of G, and the number is 10 to the minus 12 per year. One of the things that we've learned is to think of G as a field, and there's this whole route you can go down if you think of it as a scalar field, but modifications of G can arise in many different situations. And in terms of observations, there's quite extreme stuff that we can look to, which will teach us more about G. Thank you.